Let's just basically give you an overview of a typical linear regression question, at least the early stuff. And we'll do a couple more that are just like this from the homework. And then we've got one last thing to deal with, which is called residuals. And we'll look at them. And that will be us finished. So is there any general questions you want me to answer before we get started? Okay, so let's suppose, and I'm keeping the story nice and vague, that you were given some information that would be in the form of a table, and X could be age and Y could be the height of the child, or X could be the weight of a car and Y is its mileage, whatever it might be. And you got a scatter plot. And this red line is the best fitting straight line. And we know that SALT will find these two key numbers. We call these numbers coefficients, right? So that's the y-intercept coefficient, and I would probably call that the slope coefficient, right? And so in this particular case, the best fitting line, which is the name I prefer. Can anybody remember the awkward name that the textbook uses instead of calling it the best fitting line? Starts with the word least. Any ideas? You'll see it occasionally getting mentioned. It's called the least squares line. I don't like that name. It doesn't tell you much. It has. There is a reason why it's called that. I like the line of best fit or the best fitting line. I think that's a much better label. So you got this perfect. Well, it's unique. I know my scale's weird, but that would be the y-intercept, and that's 3. And if you did the little rise over run, wouldn't you get a slope of 2.1, which is kind of math 99 stuff? So what happens next then? Well, again, you would type in your data and SALT would tell you that guy, 0.82, or you would be told it. More likely you'd just be told it. Then there's a new guy called R squared. I don't think this book has mentioned this name, but I think I should tell you in case you see it if you go online and you're wondering what's going on. So if you ever see the phrase coefficient of determination, I know it's a bit of a mouthful, they're talking about R squared. Now, it's easy to get R squared. Don't you just multiply R by itself? So as a name goes, that's a pretty good name, right? R squared. Now, this decimal gets converted into a percentage by multiplying it by 100. And what that gives us, this new number, this R squared number, it gives us the explained variation, and what's left is the unexplained. So in my particular model here, about 67% of what's going on can be explained by this straight line, right? You can think of that in different ways, in different contexts. One of the, it's not very precise way, is it's like a 2/3 fit, right? 67%. It's about 2/3 of the time it's going to be pretty good. Of course, 1/3 of the time it'll probably not be so good. You can also think of as whatever X is, 2/3 of the reason why Y is what it is, right? 67% of the time is because of X. So can you imagine a situation where you might be looking at the weight of a car? Let's pretend that's the weight of the car. Or, oh, bad choice. Yeah, okay, weight's a bad choice. Age of a child and weight of a child, how about that, right? Then 67% of the factor is just the child's age. And then you say, well, what's the rest? What's the other unexplained amount? Genetics, health, and simple things like, in some countries, nutrition. A reason a lot of people from poorer countries, and not everyone is, but a lot of them are small in stature, is because there's not an awful lot of food in many of these countries. And you know, your body is, when you're young, your body's like a building machine, right? Shove food in, body gets bigger, right? Not quite that, but that's the gist of it. So if there's plenty of food, a child will typically grow to whatever the natural height of that child was going to be. But if there's a lack of food, their height tends to get stunted. So you could say that 32% was made up of genetics, health, and nutrition. And so you could break it down, as they do in fact advanced statistics, is that you do a multi-linear situation where you don't just have X, you then say, okay, let's factor in wealth, you know, and nutrition, let's factor in genetics. And if you do a really, really complicated model, you can virtually explain why that child is the height that child is by just saying they're this age and this and this and this, and those together pretty much cover everything. So you got R, you calculate this by squaring it. That tells you two guys called the explained and the unexplained variation. And then lastly, you get a question which basically says, use your formula to do a prediction. In this case, assume or try and figure out what it might be at that point there at 3.5. And you can imagine going up here, you'd hit the line and you'd go over here. That's the y-hat. And you do it simply by taking the equation, predicted y is 3 plus 2.1x, and it becomes 3 plus 2.1 3.5s, which I hope is 10.32. And that's pretty much a standard linear regression question. The x and y's will have a story attached to them, but that's the gist of it. So, any questions before we look at the homework? Looking good? Okay. So I'm going to move over to. Okay. Since someone with 100 grand, we're going to do. I will mute everybody. You don't need to hear private conversations. And we will go here. Right. I'm assuming and hoping that you are looking at question 11. Right. Now, I've kind of started question 11, but not very precise. What you're going to do is you're going to take all these points and plot it. And I went through them and did a very rough position. And so that allows me to do the tweak. So 8.8, 9.7. If I click on this, can you see I'm a little bit out here? So I'll make that 8.8 and 9.7. So the first time round, can't you just be your best guesstimate of its location? Right, the second point is 9.2, 18.8. Got that? Make that 8. Go to the third point. Should be 9.7, 20.6. That's it fixed. Go to the fourth point. Should be 8, 10.2. That was quite a bit out. Go to the fifth point. Should be 8.3. Which is that. I don't know why it's doing all these padded zeros, but we'll just have to figure that out or ignore it. Put that in. And for completeness sake, I might as well do the last one. Whoa, that was bad. The last one should have been 8.7, 13.1. Is that the last point? No, it's not. Okay. That's better. 8.7. Oh, I didn't quite get that last guy.
You can also drag the dots and it will show what the numbers
are. That is correct. Let me close these up for a minute. and show what she just said. What dot's this one, right? If I hang over this dot, it says 9.7, 20.6, which I think is actually the right location, right? But let's say that dot, right? Let's say I had placed it there, right? So it's a little bit out. If you put your mouse on it, and I think it's the left mouse button in my case, as you move it around and you look really faintly, you can see, hey, darn it, that's not what I meant to do. Go away. Delete that point. There we go. Make sure that you're on the arrow before you do any of that, otherwise you just generate a whole load of image points. Right, now I can do it. It should be 9.6, so kick it over a little bit, and it should be 20, is it 9.7? Yeah, click it over a little bit more, and let go when it's in the right place. Now, I don't know if you could see the coordinate. It was very faint in mine, but that works totally fine. Okay, so that's probably going to be time consuming rather than difficult. Just takes you time to do it. The second bit's dead easy because this data, meaning this stuff here, is basically these numbers, including the R, which I'm just going to put here. And that's that done. Make sure it's the right number. It is. Can you imagine putting all these guys in? Right. Now we get to part C, which is pretty standard. I need X bar, I need Y bar, and I need this. And these two guys are the A plus BX that we need. Before I do that, let's do X bar and Y bar. And I think last time I figured out a shortcut. There's 1, 2, 3, 4, 5, 6 numbers. If you do sigma X, that guy there is what they add up to. So I just need to take that total, which is 52.7, and divide it by 6. And the mean is 8.78 and lots of threes. 8.78 and a couple of threes. Now, if I wanted to get Y bar, I can just use this number here, which is sigma Y. That means the sum of the Y's. And I take 83.6 and divide that by 6, and I get the answer 13.93. The data set is so small, you could just add up all the numbers yourself and divide by 6 if you forgot to do that. Right. Getting close to this guy being finished. Let's go up and hit salt, and fingers crossed. And when we hit salt, you get this guy. Does anyone know or remember which one of those choices we choose to get the A and the B? The linear regression line thing.
Isn't it regression?
Yeah, kind of silly question. It's in the name, isn't it? Right, so hitting it. There we go. X is, oh, I should have told you what the story was. They collected data on various cities, and the X was the per capita income in thousands of dollars. So you found all the adults who lived in that city. You got their, probably the families actually, and you got their average income per thousand, right? So in some places in California, isn't that very large? I mean, just buying a house in California, so they get paid a lot. And that's this one. And then Y for each of these cities is how many doctors they have per 10,000 residents. So you can imagine rich, how many doctors? I would assume, based on our data, that the richer a city is, the more doctors they have. So there's probably a connection. So, oops, put them in the right way. The explanatory variable is X, the response variable is Y. And the guy we want is A and B. A is the intercept, so it's that number. And B is that. There are lots of other stuff there that you don't have to worry about. The only two numbers you're going to worry about is the x-intercept, which is going to be your A, and that guy is going to be your B. So, I've lost my place here. Where's the question? Oh, here it is here. So, A was, copy and paste it. That guy. And B, copy. And I've been caught out before here about how accurate they want it. But I'm paying attention this time. 4 decimal places, which is perfect, right? Because some questions they want 2, right? And some they want 4. And if you give 4 when they want 2, it'll probably tell you you're wrong. That's how pernickety it is. Well, if you look at this particular straight line, think of that as the y-intercept, and think of that as like the slope. Now, it's a positive number, so shouldn't that mean slope uphill? And this guy here is negative 44 very roughly. So I am looking for a line that is sloping up the way and is round about negative 4. And I want the number that's closer to negative 43. So the two that are sloping up the way is this one here, right? And this one here. Would you agree this one here, the y-intercept, is pretty close to the number it should be? And although I can't say for sure, would you agree that's more likely to be negative 20 something rather than negative 40 something? So there are little subtle clues. So you pick the right picture. Now, the next job is going to use this number. That's called the correlation coefficient. Oh, before I move on, how good is 0.86? Is it strong or moderate? Or is it kind of somewhere between the two? 0.86.
Moderate?
Yeah. 0.9 or above is normally strong, right? And 0.7 is about, the moderate. You could argue that it's moderate to strong, and that's fine because there is a lot of grey area. So I've got this guy. Now, how do I get R squared? Well, I take that guy, and I square him. So that's just a placeholder so I can type this fella in now. 0.8686 when you square it, right, is about 0.7544, and a whole load of the other stuff. Now, we want this rounded to 4 decimal places, but it's 446, which means I need to remember to round it up. And even a little thing like that will catch you. Do you know if you say 44, it'll say you're wrong. And you'll be scratching your head because as far as you can tell, you're right. Well, you're almost right, but you're not right enough. Now, explained is going to be to 2 decimal places. So 75.45, which is basically that guy turned into percentage. So about 3/4 of the variation is explained for in the model. That's what that is. And that means the rest, which is what, 24.55% is unexplained. So in layman's terms, this particular model, if I return back up to this picture here, if you drew a straight line through it with the equation they just gave, right? That straight line is about a 3/4 fit, right? 3/4 of the time you get a data point or a prediction that's pretty close to the real answer. And a quarter of the time, it's probably not that good. And the last one is, suppose a small city in Oregon had a per capita income of 9.9 thousand. Let's figure out what the doctors would be. That's basically take this equation and put 9.9 there, right? Instead of the x. So though you can't see it, I'm typing it in. So I'm going negative 43.7949 add 6.5763 times whatever x is. And x is 9.9. And the answer that I have to 2 decimal places is 21.31. So about 21 doctors per 10,000 residents. Right, so what would that, if you divide that out? It's about 1 doctor for every 500 people. Not bad. If you go to some other countries in the world, it could be 1 doctor per 10,000. Right? You got your, an impoverished country. So, are we cool about this process from start to finish? Did you notice I didn't even really, or I should have, I didn't even get into the story because the math was the same regardless of what the story was. And it was only towards the end I said, well, hey, we should really look at what this data is about. Theoretically, couldn't have done that entire question and not even bothered to look at doctors or Oregon or anything else. Right? It could have done everything just based on what it's been asked to do. Do a quick check. Yeah, okay. We only have one more of these types of questions to do. Do you want me to do another one of these, or can we call it good and we can move on to the last thing, which is residuals, which is new stuff? Does anybody want me to do 12, or are we good to go? Last chance.
Can you show 12?
Good, let's do it. I'm going to cheat a little bit because I'm lazy. If you take this data and you plot it, can you pretend that you get dots that look like that? Right? I'm not doing it, but you can imagine. So step 1 would be do a real correct dot plot, right? This step 2 is exactly what every other one is because the numbers are here and we've got them. And we don't really need to do them from scratch. They would take forever. There we go. Now, X bar and Y bar, I will do some, oops, picked up an extra decimal point. If you take 1, 2, 3, 4, 5, 6, if you take this guy and divide them by 6, you get 15. And if you add up all the Y's, you get that number. And if you divide that by 6, you'll get the average. So 8.1 divided by 6 is 1.35. So that's where they came from. Now, the A and the B, the y-intercept and the slope, that's when salt kicks in. So we're going to go to regression. The first variable is number of research programs and how many patients there are. And the 2 guys we're interested in, A is the intercept coefficient and B is the slope coefficient. So that's going to disappear for a minute. If I go down where those answers go, the y-intercept is that number. The slope intercept. I know it looks kind of clunky. It says plus, but it's a negative number. I mean, that plus is fixed. It's printed. I can't rub it out or anything. So just live with that. If you think about it, even although my dot pattern is pretty bad, would you agree it's a negative line? So it kind of does fit the data. One of these four is this guy. Let me shrink it up a little bit so you can see all four, hopefully. Which one of those, top left, top right, bottom left, bottom right, is the 2.9 minus 0.1043x? Which one?
The bottom right.
Here, a bottom right. So I'm clicking on that. Would you agree that the y-intercept is the right number? Would you agree that that y-intercept is 1.9, not 2.9? So that's why it was this one and not that one. Because I think the pattern is 2 sloping up and 2 sloping down, isn't it, in every combination? So you normally only need to look at a choice of 2 pretty quickly, and then the y-intercept seems to be a good guide. Now, I'm going to copy this fella for a minute. He's just going to be a placeholder so I can put him here. Is this guy a strong linear correlation, moderate or weak? What's this one?
Because of it being negative, would it be weak because it's less than the whole number, or?
No, we don't care if it's plus or minus. The
Okay.
plus or minus just tells me it's strong positive or strong negative.
Oh, then it's gonna be strong.
It's going to be strong, yeah. So it's not how big the number is, positive, negative. It's just how big the number is, regardless.
In the direction it's going.
Yeah,
Gotcha.
in the direction it's going. So that's darn close to being -1. So it is a strong one. Now, r squared is going to be this guy times itself. Before I even do that, is that answer going to be positive? If you take negative point and multiply it by itself?
Yep, it'll be
Yeah.
it'll be a positive.
It'll be a positive. And it ends up being positive 0.8506. How many did they want? 4, right? So that's what I do with that one. The next digit after the 6 is a 3, so I'm leaving it as a 6. Which means that r squared is always positive. Because if it was 0.8, you'd get 0.64. If it was negative 0.8, you would still get 0.64. That means that 85.06% is explained by the model. And the bit that's unexplained is 14.94. Are we good with that? Now, there is a little equation up here that I'm going to have to keep. That's this guy here, right? And we're being asked, suppose, now I haven't even looked at the story. So here's the story. Suppose a pharmaceutical company has 14 different research programs. What does the model predict the average number of patients per program? So they have just told me X. They've just told me that guy. So let's find out what the predicted Y, which is how many patients in each program. 2.9143 subtract 0.1043 times, I believe it was 14, double check. Yeah. And I get I don't like that answer. But it's correct. It's very small. If you look at the straight line, can you see that when you've got about 14, isn't the answer 1 and a bit? I can't horizontally draw. I could check my decimal again. It is 2.9, isn't it? Yeah. Take away nothing 0.1043. It is 14, right? Sometimes you just have to trust the math. If it says it's the number, go with it. What can I do here? I'll make up a story for why it's unrealistic. Do you know the WebAssign randomly generates numbers? Can you imagine it just randomly generated unlikely numbers that gives unrealistic answers? Right? The process is correct. I don't see the whatever. These are very small numbers. So unless these numbers mean something more than the average number of people, I'm not very convinced about what's going on. Okay. So we have 2 more questions and we're finished. And they're to do with a thing called residuals. Well, basically I can use this one, although it is a question, because it's got a lot of the stuff I want in it. So it says, look, the best fitting straight line usually does not go through all the points. Well, duh, of course not. It'd be a perfect line if it did, right? It goes through most of the points closely, would probably be a better description, right? But under some points, quite a bit away, right? No matter where you draw the line, that's kind of going to happen. So there's usually a difference between what the straight line says, that's a predicted value, right? Where it is on the straight line, and where it would be as a real data point. So let me kind of show you visually what they're getting at here. Now we'll return to this. So can you imagine? Actually, I can use this guy. Nah, too messy. Let's start a new one. So we collected our usual data. And here it goes. We've got dot, 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 dot. Maybe give you a couple of out of the way guys. And the best fitting straight line is that line, right? Now, if we choose that point there, right? Isn't that a perfect match? That data point, right, where that big solid one, isn't that got the right Y value? Because both the line and the real data point match. But most of them are only close. Some are really close, and a few, like these 2 in particular, aren't that close at all. So we have a table. So can you imagine I collected a table that's going to have 4 columns in it. And you might get something like, can we pretend that this guy is 6, 15? So you get 6 and you get 15. Y hat is what the straight line would say, which is 15. And Y take away Y hat. So Y is the data, take away the predict. In this case, it's a perfect match, so it's nothing. Can you imagine I get another point, 7. Let's say 7 was this dot here, right? Actually, I'm going to have to change this then. No, that was right. Let's say 7, which is this dot, and we got 21. But the straight line said 23. Do you see there's a little difference between the data point and the straight line? This y coordinate is y hat, and this y coordinate is y. Do you see they're slightly different from each other? So in this case, if you take the y, take away the y hat, you get -2. Imagine I did another one at 10 and another one at 3. And here it was 4, it was 10, and that was 7, and here it was 6, and that was 5. Let's see what we would get. Y take away y bar is 1, 10 take away 7 is 3. These guys here, the difference between the data and the predicted. Right? So the difference between the data and what the straight line predicted it should be is called a residual. Now, residuals are quite useful things to calculate. One of the things they tell you is, in one way of looking at this, isn't a residual an error? How much you got, how much you were wrong. I predicted this, but it was really that, you know, that kind of situation. In this case, the data, take away the thing, this is a prediction where it was, what, -2, right? In this case, it was, you predicted 2 short. In this case, you predicted 3 too much, right? So you underestimated by 2, you overestimated by 3, right? That's kind of what a residual is. How much did you under or overestimate by? What they tend to do with these guys is they draw a plot called a residual plot. And the x-axis, and there will be a y-axis. And the y-axis has the residuals in it. And the x-axis are the normal x-axis. So what have I got? I've got up to 21. So you can imagine 5, 10, 15, 20, something like that. And so when x is 6, the residual was 0. So you put a dot at 0. When x is 7, the residual was -2. So when x is 7, the residual was -2. Imagine it would be this dot. When x is 10, the residual was +1, which would be about here. And when x is 3, the residual was +3, and it would be about here. Now, can you imagine I did, for every single one of these points, I calculated the residual. What you would get might look something like this. Right? Can you imagine what a residual plot? It wouldn't have, you wouldn't expect it anyway, to have any particular pattern. There's no reason why it would be a straight line. At least it shouldn't be. Because if you plot a residual diagram, and the dots are pretty randomly above and below the line, and there's no discernible real shape going on, maybe I should put one more here just to make that more obvious, right? Then you could be pretty confident that this fella here really is a straight line. So if residuals centered at 0 are randomly distributed, can you imagine zigzagging up and down, then what you can say with a fair degree of confidence is that the model is linear. Can you imagine a different set of data? And the residual plot looked like this. Do you see a distinct linear pattern here? You see it, the residuals? That's bad news, because if you see any kind of pattern that's a strong discernible pattern, it means that this data isn't actually straight. It might look straight because the human mind is kind of hardwired to see straightness or patterns. What it's really telling me is that this data is probably curved. But not obviously curved, like it's going like a banana curve. I'd see that, right? But nonetheless, it's still curved, which means that you probably shouldn't have been doing linear correlation. So you might say, well, what do I do? Well, the great thing is that there are lots of correlation curves. Linear is the only one we deal with because that's what we're doing in this class. But do you know there's quadratic regression? That's what it's called. Cubic regression, exponential regression, logarithmic regression, and a whole load of others I can't, I'm making one up. Square root regression. I bet you there's a square root where you fit the best fitting square root graph through the data points. So all that would say is my model's not good enough to be straight. I'll go and see if I can find a different curve of some kind that might be a better fit. And you do the residuals on that. And so it doesn't matter what the model is. The residuals, if they are random like this, means you've got a good fit, whatever curve or straight line in our case is going to work. You do not want any kind of pattern. Do you see happy face shape? I see happy face shape. Bad news, not a linear model. Don't know what it is, couldn't even guess, but I know it's not linear. That's basically it. You see how residuals work? Now, you can calculate a single residual, right? So let me show you by hand how we would do that. It's normally done by software because it's very time consuming and laborious, but just so you know how the software is doing it. Let's suppose I collected all my data, right? My X's and my Y's, and I won't write all the data down. I'll just write one of them down, that one, right? And I got the equation, and the predicted Y was 2 plus 0.4x. Okay, so that's my straight line. To calculate the residual at that one point, right, at this guy here, Y hat is 2 plus 0.4 times x, which in this case is 2 plus 1.2. This is 3.2. So y take away y hat is 7. Take away 3.2, and I am left with a 3.8 residual. So that is how you find the residual at any given point. Now, can you imagine that there's eight different points here? Couldn't you do this 8 times and find the residual each time and plot it? Now, if I wanted to do that, and I'm only doing it for one point, the residuals are always going to be centered at 0, right, and plus and minus. Can you imagine at x equals 3, I would do 1, 2, 3, 4. I would do a dot about 3.8, and that's where the residual dot for that one guy is. Now, can you imagine I did it then for all of them, and it ended up looking like this. Put one more in, yeah. Would that be a good residual plot? Would that mean it's linear? Yeah. Would you agree that's just ziggy-zag random?
Quick, Professor.
Yes.
So sorry, how are you getting picking the x value again?
Oh, in the table, the x is 3.
Oh, okay.
Right? So can you imagine there was a 5, a 7, a 9, an 8, a 4, a 2, and whatever. For every one of them, I would plug in this guy to get the y hat. So you can imagine there would be another row here called y hat, which is what the straight line would be predicting. In this case, it would be the 3.8. Right? And it's the difference between this guy, take away that guy, is what we call the residual. Right? The real answer in the data minus the predicted. Any questions about that? We go? Right. Oh. If the residual numbers are 4 to -4, it is linear, but they're quite big errors, aren't they? Can you imagine I got a residual plot that looked like this, but the numbers went from 0.1 to -0.1? Wouldn't that say, yes, you are linear and you're very good at predicting the right answer? Wouldn't this be, yes, it is linear, but you're very bad at predicting the right answer? So you might get this with a 0.6, and you might get this with a 0.89. Do you see the difference? Both are linear, both are residual models, but one situation may generate larger residuals than the other. And that's caused by accuracy of the model, how good it is at fitting the data. So let's look at the only 2 homework questions there are, and that will be us. Well, I'll talk a little bit about other things, but that's us as far as that's concerned. Right. So they're basically talking you through what I just did, right? So here is what the residual plot looked like. Can you see it? Now, looking at that picture, I think I should make it a little bit bigger because I don't know what your screen's like. Okay, yeah. It may be overkill. Okay, that'll have to do. Is the least square line providing a reasonable model for the data? Right, when you look at this data, does it look, and sometimes it's a bit of a subjective decision here. Does this data look like it's pretty random, or do you see some kind of pattern? I have problems with this data set because my brain is wanting to make a very, very bad happy face, right? And yet my gut feeling is it's probably not that happy. For instance, if I just put 1 dot there, or 2 dots, say 1 dot there and 1 dot there, wouldn't the happy face totally disappear on you? So I'm not 100% sure. So I'm going to go up and ask it to tell me. Is it 13, I think? Here we are. Yeah, they are saying it appears to be random. So I think they're going to do it where it's darn obvious it's not random, right? It's going to look like a vertical, a diagonal set of dots virtually going downhill, right? Or a very obvious happy face, or something that is clearly not random. And so that's fine. I'll take that. If a point on the residual plot seems far outside of the pattern compared to the other points, it might reflect an unusual data point called an outlier. And we've talked about them before, right? Such points may have quite an influence on the least square model. They do. Can you imagine an outlier screws up with means and standard deviations? Can you imagine it could screw up with the straight line equation? And it does. Do there appear to be any outliers? Now, how would you be able to tell an outlier? Well, the first answer is there isn't any obvious outliers. But if you wanted to see what an outlier looks like, I'm going to draw one right now. And I don't want that pen because it's not easy to see. If you can just bear with me, I'll be doing it in a second. This is a situation where there is an outlier, and I'm trying to show you what that would look like when you did residual, right? When you tried to do a residual plot. Now, there's the original data. Can you imagine this guy here as an outlier? What that guy would look like if you did the residual plot. Remember the residuals, the difference? You'd have a whole load of random data like this, right? And then one really bad outlier dot. So in that case, can you see that the outlier on the original data will look like an outlier in the residual data? Does that make sense? That you can see, because can you imagine the straight line? That would be miles away, right? And that's reflected on this number here, right? So actually that went pretty smoothly because I saw some nodes. So it made sense, right? Outliers, residuals should be weird looking most of the time. So I think this is the final question. It is. Okay. Here is some data. Here is the equation. And we are going to get a residual plot. Okay, fingers crossed. Use salt. Go here, probably shrink it down a little. Okay, hit regression.
We can't, or at least
Oh,
I
you can't see it?
you.
Okay, thanks for telling me. I forgot to switch over. Here we go. Right, so I'll kind of show you what I did before I did it. Right, so the last question, we've given some data, but even tilled the least square line. And here are the four possible guys. Now, I should have done this earlier, but I forgot to. So I hit salt, and this guy appears. Pick regression. I should be able to go X and Y. Okay. Oh, it might be somewhere else. No. No. I should have checked this before the class comes. My apologies.
There, right up at the top, it says right next to the main scatter plot.
Oh, there it is. Yay, thanks. Somebody's paying attention instead of me. I was going to say, why would they ask me to do salt if I couldn't use it to do what I wanted? Now, I'm going to have to shrink this thing down because it's just, there it is. Can you see the scatter plot? I shouldn't say scatter plot. Can you see the residual plot, right? There is 0, and there's not an awful lot of dots here. They're like, what, 3 above and 5 below, and they're kind of sort of a pseudo random, but at least I've got that. Now I'm going to try and keep that picture in my head, and then I'm going to go here, and from what I have, which is easier for me because I can look at both, that the guy that looks closest to what I've got, oh, there it is that one. The picture they give you is this size. The picture and the thing is that size. So all the scales are distorting the width and so on. And they're being very generous here. They're saying that's pretty random. I guess if you put one dot where my mouse pointer is, wouldn't it look very random? So again, I said that, I'll repeat it. If it wasn't random, can you imagine the data looked like that? Then that would be no good, right? And you would say the residuals do not seem to be scattered randomly, and there do not appear to be outliers, right? Well, let's do that. The residuals do not appear randomly and do not appear to be outliers. The residuals seem to be scattered randomly. Like, so you would say one of these two, and then you go looking for outliers. I can't see any outliers in any of these four pictures. If there was an outlier, can you imagine it might be a dot up here somewhere, quite distinctly different. Are we good? Right, so, any questions before I kind of finish off today with just information? Right, will you all say hi to get attendance? While you do that, give me a chance to get myself organized. Are we good? Is that everyone? No, a couple of people still saying hi. There's Ripken. Oh, we're all getting into the Christmas mood now. You know, I'm not just getting highs, I'm getting hee-hi hoes and who knows what else in here. Santa Claus highs. I got you, it's Christmas, you're getting into the mood. Okay, I'm assuming that's plenty of time. So, information. Monday is review for final. So you turn up on Monday, we'll go over anything that you want me to go over. So if you want me to do, I have no idea, hypothesis testing between two proportions, we could do something like that, you know, a question or two, or whatever you want. Monday is totally open-ended, right? It's about whatever you want, whatever you feel is necessary. I have it in front of me here. When is our test? Final,
Friday,
I should say.
Friday, right?
Friday.
Friday.
And Friday from
1
to
to
4.
3?
1 to 4.
1 to 4.
Right. Now, the test typically would, according to WebAssign, because I let WebAssign tell me this, because it's collects data on how long students take to answer a question. It will be designed to take 2 hours.
Oh my God.
So the fact you're getting 3 hours is just to make your life a little bit easier,
Is
so
it
that you can take your time and not feel rushed. Question?
is it from the midterm to now, or is
Nope.
it the whole quarter?
The whole quarter.
Okay.
It'll be slightly more weighted to the second half, like 1/3, 2/3 kind of thing.
Okay.
But it'll still contain questions from everything, right? It's chronological order. So your first question will be from week 1 and your last question will probably be, will be linear regression stuff, right? Are we cool with that? There will be, oh God, I'm trying to remember. There will be 20 questions. I believe it's 20. It's 15 or 20. I believe it's 20. I'll tell you what I believe it is. It's going to be 20 questions. And they're all worth 15 points just to make life simple. Some 15-point questions are very quick and are easy to get 15 points. Others, you'll have to work at it. SALT will be available. It will look just like your midterm. So you'll turn up, there'll be a Zoom meeting so I can see you all, and I can answer any questions that might come up because something doesn't work. It will appear at 1. You'll have until 3 to finish it on WebAssign. You'll then get 30 minutes to take pictures, you know, Adobe Scan on your camera, and upload it into Canvas like you did in the midterm. So hopefully you're all comfortable with, you know, taking pictures, turning it into PDF and sending it to me. When you're doing these questions, and it's kind of hit and miss with WebAssign. You know, some of the questions today, didn't you just look at 4 pictures and pick the right one? So there's no working you can really show me. But for any other question, anywhere that you can show me some working, will you do so that we can give you partial credit if you get it wrong? If all I see is the wrong answer and I don't know where it came from, it's going to be hard for me to judge that. Now, if you're doing the salt button and you pick the wrong picture, then it's your fault. I mean, you picked the wrong picture, so you can't really get partial credit for that. But if it's stuff that involves you doing calculations, that would be really helpful.